In this module, we shall learn about the estimation properties under simple regression analysis. Let us begin by understanding the meaning of regression. Regression is one of the most powerful tools in statistics. Regression analysis is a mathematical measure of the average relationship between two or more variables in terms of their original units of the data. In regression analysis, there are two types of variables. The variable whose the value is influenced or is to be predicted is called the dependent variable, and the variable which influences this dependent variable is known as the independent variable. More specifically, in regression analysis, we can understand how typical values of the independent variable affect the dependent variable, and how the independent variable varies, and along with it the dependent variable also varies, while the other independent variables are fixed, held fixed. So this is the main purpose of regression. If the given bivariate data is plotted on a graph, the points so obtained around the scatter diagram will be more or less concentrated around a curve called the regression curve. The mathematical equation of the regression curve, usually called the regression equation, enables us to understand the average change in the value of the dependent variable for any given change in the value of the independent variable. If the regression curve is a straight line, then we say that there is a linear relationship about the variables under study. In the case of linear regression, the values of the dependent variable increase by a constant absolute amount for the unit change in the value of the independent variable.
After studying this module, you shall be able to outline the assumptions on which the classical normal linear model is based and understand the significance of these assumptions. Learn about the desirable properties of the OLS estimators A hat, B hat. Learn about the statistical properties of the OLS estimators A hat, B hat. Let us begin by understanding the assumptions of classical linear regression model. The Gaussian standard or classical linear regression model, that is CLRM, which is the basic framework of regression analysis, makes 10 assumptions. These assumptions are: Assumption 1. Linear regression model. The relationship between the regressant, the regressor, and the random disturbance is linear in the parameters. However, the regressant y and the regressor x themselves may be non-linear. Therefore, the term linear regression will always mean a regression that is linear in parameters. That is, the parameters are raised to the first power only. It may or may not be linear in the explanatory variables. Assumption 2. X values are fixed in repeated sampling, or X is assumed to be non-stochastic. Assumption 3. Each value of xi and of y is observed without measurement error. Assumption 4. The sample variance of x is different from 0 and has a finite limit as n tends to infinity. Assumption 5. The parameters a and b are fixed. Assumption 6. Zero mean value of disturbance ui. Given the value of x, the mean or expected value of the random disturbance term ui is 0. Technically, the conditional mean value of ui is 0. Symbolically, we have expectation of ui given xi is equal to 0. It means that the distances above and below the mean values, which is ui, the deviations, and the assumption requires that the average or the mean value of these deviations corresponding to any given x should be 0. Assumption 7. Homoscedasticity, or the disturbances have a constant variance. Given the value of x, the variance of ui is the same for all observations. That is, the conditional variance of ui are identical. Symbolically, we have variance of ui given xi is equal to sigma square. In other words, the variation around the regression line, which is the line of average relationship between y and x, is the same across the x values. That is, it neither increases or decreases as x varies. Assumption 8. No autocorrelation between the disturbances, or we can say that the values of u are serially independent and their covariance is accordingly 0. Given the values of two x values xi and xj, where I is not equal to j, the correlation between any two ui and uj where I is not equal to j is 0. Symbolically, covariance of ui and uj given xi and xj is equal to 0. In other words, given xi, the deviation of any two y values from their mean value do not exhibit any particular pattern. Assumption 9. The disturbance u is normally distributed, represented as n0 sigma square. Thus, each disturbance term is normally distributed with mean 0, variance sigma square, and covariance between two disturbance ui and uj is 0. For two normally distributed variables, zero covariance or correlation means independence of the two variables. Thus, with normality condition, ui and uj are not only uncorrelated but are also independently distributed. Assumption 10. Zero covariance between ui and xi, or E of ui xi is equal to 0. This means that the disturbance u and the explanatory variable x are uncorrelated. Given the assumptions of CLRM, the OLS estimators are given by B hat is equal to summation xi minus x bar into yi minus y bar upon summation xi minus x bar whole square, and A hat is equal to y bar minus b hat x bar. Knowledge of these assumptions provide the necessary knowledge of how to properly use OLS. Moving on to the desirable properties of OLS estimators. Before examining the properties of OLS estimators under the statistical assumptions of the CLM, we pose the following question. What are the desirable properties for an estimator? The three desirable properties are: first, unbiased estimator; second, Gauss-Markov theorem; and third, the ability to perform statistical tests. If these occur, the inference process will be carried out in optimal conditions. Let us first understand the meaning of unbiased estimator. Mathematically, unbiasedness of the OLS estimator is expectation of B hat is equal to B. The estimator B hat is unbiased, that is, its expected value is equal to the parameter that is estimated B. The estimator B hat is a random variable. In the figure, the density functions of two hypothetical estimators obtained by two different methods are shown. The figure on the left shows the case of unbiased estimator, and that on the right shows the case of biased estimator. In the left side of the figure, two estimators of B, that is B1 hat and B2 hat, are obtained. The first estimate is relatively close to B, while the second one is much farther away. In any case, unbiasedness is a desirable property because it ensures that on an average the estimator is centered on the parameter value. In the right side of the figure, the estimator B hat is biased since its expectation is not equal to B. The bias is precisely expectation of B hat minus B. In this case, two hypothetical estimates B1 hat and B2 hat are represented in the figure. As can be seen, B1 hat is closer to B than the unbiased estimator B2 hat. But this is a matter of chance. In any case, when it is biased, it is not centered on the parameter value. An unbiased estimator will always be preferable, regardless of what happens in a specific sample because it has no systemic deviation from the parameter value. In each sample of y's, the x are fixed in a repeated sample according to the assumption 2. B hat takes a different value, but on an average is equal to the parameter B, bearing in mind the infinite number of values B hat can take. In each sample of y's, a specific value of B hat, that is to say, an estimation of B hat, is obtained. Moving on to the statistical properties of OLS estimators, we have first linearity of B hat. The OLS coefficient estimator B hat can be written as a linear function of the sample value of yi. That is, B hat is equal to summation xi upon summation xi square. The proof can be as follows. B hat is equal to summation xi into yi minus y bar upon summation xi square, which can be written as y bar into summation xi upon summation xi square, which is equal to summation xi upon summation xi square. We can write the above expression as B hat is equal to summation ki yi, where ki is equal to xi upon summation xi square. Thus, B hat is a linear function of the sample values yi, where the coefficient of yi is ki. The next property is unbiasedness of B hat and A hat. That is, expectation of B hat is equal to B and expectation of A hat is equal to A. Moving on to the next property, we have the variance of the OLS slope coefficient estimate B hat is defined as variance of B hat is equal to expectation of B hat minus B whole square. Now coming back to the equation on square of sampling error of B hat, we have expectation of B hat minus B whole square is equal to summation ki square uy square, where I ranges from 1 to n, plus twice of double summation ki ks uy us, where I is less than s and s ranges from 2 to n. Taking expectation conditional on sample values, we have expectation of B hat minus B whole square is equal to summation ki square uy square given xi, where I ranges from 1 to n, plus twice of double summation ki ks, where I is less than s and s ranges from 2 to n, into expectation of uy us given xi xs, which is equal to summation ki square into expectation of ui square given xi, since expectation of ui us given xi xs is equal to 0. Thus, we can write variance of b hat as sigma square upon summation xi square, which is equal to sigma square upon summation xi minus x bar whole square, which is equal to sigma square upon TSS of x, where TSS, that is the total sum of squares, is equal to summation capital Xi square. The standard error of b hat is the square root of the variance. That is, standard error of b hat is equal to under root of variance b hat, which is equal to sigma upon under root of TSS of x. Moving on to the fourth property, we have property number 4 as variance of a hat is equal to sigma square summation xi square upon n into summation xi square, which can be written as sigma square summation xi square upon n into summation x minus x bar whole square. And standard error of a hat is equal to under root of variance of a hat, which is equal to under root of sigma square summation xi square upon n into summation xi square. Further, we shall discuss the interpretation of variance of coefficient estimators. Smaller the values of variance of a hat and variance of b hat, smaller is the error variance sigma square, and larger is the sample variation of xi about their sample mean. That is, larger is the value of x square, which is equal to xi minus x bar whole square, and larger is the size of the sample, that is, larger is capital N. The last property we have is property number 5, covariance of a hat and b hat. The covariance of the OLS coefficient estimators a hat and b hat is given as covariance of a hat and b hat is equal to expectation of a hat minus expectation of a hat into b hat minus expectation of b hat. Interpretation: sigma square and summation xi square are both positive. Therefore, sign of covariance of a hat and b hat depends upon the sign of x bar. If x bar is greater than 0 and covariance of a hat and b hat is less than 0, then the sampling error, that is a hat a and b hat b, are of opposite sign. But if x bar is less than 0 and covariance of a hat and b hat is greater than 0, then the sampling error a hat a and b hat b are of same sign. Moving on to the Gauss-Markov theorem. The Gauss-Markov theorem summarizes the statistical properties of the OLS coefficient estimators a hat, b hat. The statement of Gauss-Markov theorem is: given the assumptions of the classical linear regression model, that is CLRM, the OLS coefficient estimators A hat and B hat are blue in the class of all linear unbiased estimators. The blue represents B stands for best, L stands for linear, U stands for unbiased, and E stands for estimators having minimum variance. So, Gauss-Markov theorem says that the OLS coefficient estimators A hat, B hat are the best of all linear unbiased estimators of population parameter A and B. These estimates, which are the best, will be statistically more per use.
Now let us summarize what we have studied. The statistical properties of OLS estimators are linearity, unbiasedness and efficiency. Efficiency is measured as the minimum variance property. Linearity implies that the OLS slope coefficient, that is the estimator which is B hat, is a linear function of the values of yi. B hat is equal to sigma ki yi, where ki is the coefficient or the weights. When the OLS estimators are considered, that is A hat and B hat, these should be unbiased. Unbiasedness implies that the expectation of B hat should be equal to B and the expectation of A hat should be equal to A. A and B over here are the population parameters. The variance of the OLS estimators are given as variance of B hat is equal to sigma squared, that is the variance of the population, divided by summation xi small xi squared, and the variance of A hat is given as sigma squared into small xi squared upon n into small xi squared, and therefore this would actually reduce to sigma squared by n. So if the population variance is known, the variance of both B hat as well as A hat can be found out. The smaller the variance, the larger is the, or greater is the precision or the efficiency of the OLS estimators, both alpha hat and beta hat. The covariance of alpha hat and beta hat is given by minus small x bar into sigma squared upon summation xi squared. So this is the covariance of the two parameters, the regression parameters. The Gauss-Markov theorem summarizes the statistical properties of the OLS coefficients, that is A hat and B hat. The theorem states that under assumptions of classical linear regression model, the OLS coefficients or the OLS estimators are blue. What does blue mean? Blue is a class of estimators that are the best amongst all the linear unbiased estimators. Best over here would mean the estimator has the minimum variance.